So welcome to the last lecture before the Christmas break. Last time I started to introduce additive classes, which are derived classes from the Chern class of a complex bundle, or you can do the same thing for the Montriagi classes of a real bundle. So let me briefly recall what we did. So we started with a power series called G. So that's a power series in one variable, and then we associated something for an element of a graded algebra. So we have this graded algebra, commutative, and we start with an element which I denote as just a formal element for the moment. So it's 1 plus C1 plus C2, etc. in there. So the one part is in A0, the unit. And now what we do is this: we take this element, and in applications this will typically be the Chern class of a bundle. So we take the element, apply the power series of the logarithm to it, and then we apply an endomorphism, which is degree preserving on this algebra, and which depends on the power series G to that. So this just multiplies each component with a certain multiple of the corresponding coefficient in this power series. Then we get a new element, and this element was essentially the corresponding additive class, except that there is this degree 0 term missing, because if you look at the logarithm series, this starts with degree 1. So if you insert 1 for something, so the degree 0 part is gone, so there's no degree 0 part in here. So for this reason we have fixed an integer n, which we take as the, and that's the unit in A, which we take as the degree 0 part. And this is then the derived additive class. Okay, and in applications, n will be the rank of the bundle, and C will be the Chern class of the bundle. And as an example, so this is so we can apply this procedure, and so this is called the additive class of a complex bundle, of a C bundle, where associated with this power series G, if we choose as our ring the cohomology ring of the manifold, and as our element in the ring the Chern class. So that's the additive class associated with it, and similarly we can do the same thing for real bundles. Then we have here the rank n real bundle. We can associate an element with this, where we take as AJ 4, J is homology, because this is where the Riemann classes live, and C is then the Riemann class. Okay, so we can do this both. So it's an entirely algebraic construction. We have seen one example, namely if we use the exponential series and do this for complex bundles, so using the Chern class, then this gives us the Chern character of the bundle. Not the Chern class, but the Chern character. All right. And now, because of this logarithm, the multiplicative property of the Chern class and also of the Montriagi class concerning direct sums of bundles gets transformed into an additivity property. And this is why they're called additive classes. So this is due to this logarithm in the construction. Good. So that's what we did last time. And now I want to give maybe two different descriptions of this construction, which are both useful, and it depends a bit on the context which one is the best one. So let me recall that these sigma n comma k of n variables, so this is supposed to be the kth elementary symmetric polynomial in n variables. So this is the kth elementary symmetric polynomial in n variables. And now let's redo this construction in a slightly different way. Last time I was also asked why, maybe we should consider that this lambda j, this lambda g restricted to a j was a multiple of the identity. The multiple was minus 1 to the j plus 1 times the corresponding coefficient in the power series, gj times j. So that if we write this as 1 plus g1x plus g2x squared plus and so on. So that was the definition of this endomorphism lambda g on our commutative predicted algebra. And I was asked why exactly this formula, and we will see in a moment why. And okay, so let's see. Given this polynomial, or this power series rather, I can do the following thing. So let me take this power series G and insert any of these variables xj into it. Then this is a power series in the variable xj, and I can add over all variables. Then I get a new power series. This time it's a power series in the variables x1 up to xn. And clearly by construction it's symmetric in all the xj's. So in particular, each homogeneous part is also symmetric in the xj's. So if we, so that's a power series. So that's now a power series in the variables x1 up to xn. It is symmetric in x1 up to xn. So in particular, we can take a homogeneous part of this power series of some degree. So we take a homogeneous part of degree k of this power series. So that is supposed to be homogeneous part of degree k. Now this becomes a polynomial in x1 up to xn, which is homogeneous of degree k. And for these polynomials, we know that we can express them in a unique manner as a polynomial in the elementary symmetric polynomials. So there exists a unique polynomial, which I would like to call alpha k, such that this one is the polynomial alpha k of the elementary symmetric functions of the x's. So it's sigma 1 of x all the way up to, and since this is of degree k, the highest one that is appearing here is sigma k of x, right? And so this is a polynomial in k variables here. This is x of s1 all the way up to sk. So this elementary symmetric polynomial of degree k that we have on the left side can be uniquely written as a an expression in the elementary symmetric polynomials, sigma 1 up to sigma k. And this is the polynomial alpha k that we get from, yeah, sometimes it's called Newton's theorem on elementary symmetric functions. Right, good. So we have that. And now let's see. The first remark I want to make is that I did not insert the n in the definition of the alpha case here. And there's a reason for it, because it does not depend on n, as long as n is at least k. So let me make this as a first remark here. So alpha k does not depend on n as long as n is at least k. And that's something we will always assume. And why is that? Well, let's do the construction for two different n's. Namely, so let k n, so n1 be at least k, and another one, which I call n2. Now we can do this construction. Let's do it first for n2. So then what do we get? Then we get this homogeneous part. And now I have to sum from j to n2 here, g of xj. And this will then be given as alpha k of the elementary symmetric polynomials for n2. Yeah, so in n2 variables. Alright, and now what I do is I just put all, so I want to come now to n1, so all the variables that I do not have in n1 anymore, I would just put to 0 and see what happens. Okay, put xn1 plus 1 all the way up to xn2 equal to 0 in this equation. In this equation here. Now what will happen then? All right, then we have the homogeneous part of degree k of the sum of g xj. Now, well, if I insert 0 here in my power series, of course I get 0 for the corresponding term, except in degree 0. But we are not looking at degree 0 here. That's fixed by the n anyway. So k is at least 1. So that means if I insert x0 here in the g, the corresponding summand of the sum actually disappears. So that means now I sum only up to n1 on the left side. That's what we get here. And on the right side, we get alpha k. Now I insert, I have n2, 1, and I have x all the way up to xn, followed by zeros, right? So this. So this is, so that's x1 all the way up to xn1, and this are the remaining zeros. n2 minus n1. So I'm going to look for the others. And what happens if you insert the zeros for these last variables into an elementary symmetric polynomial? Well, then you just get the elementary symmetric polynomial in n1 many variables. So that is the same thing as alpha k of sigma n1 over 1 x, and so on, sigma 1 k x. And so we have the same alpha k both for n2 and for n1. So the alpha k does not depend on n. So that's what I want to say. So associated to this power series G, we get all the alpha k's here. And the alpha k's are polynomials in more and more variables. K variables for alpha k. So definition, the sequence of polynomials alpha k, k starting with 1. So this is called the additive sequence of the power series G. And why is this? Well, let's do an example. Maybe the important example, but G is the exponential series. And all right, so let's compute alpha 1 and alpha 2. In order to compute alpha 1 and alpha 2, I need to take at least 2 variables, right? So the number of variables must be at least as large as the k I want to compute. So let's take 2 variables. I want to compute alpha 1 and alpha 2. So we choose n at least 2. So let's take 2. Why should we take 2 n? Now, let's see. So what do we have to do? We take the sum of the power series. So in this case, it's just 2 sums, and G is the exponential series. So we have e to the x1 plus e to the x2. So that's what we get here. And if we write it down, then we get 1 plus x1 plus x2, x1 squared on 2, and so forth, in higher terms. For the first thing, plus 1 plus x2 plus x2 squared on 2 plus higher terms. Or maybe we should also, yes, that's what we have. And now so all the remaining terms are of degree 3 at least, which are of no concern if we only want to compute alpha 1 and alpha 2. So what do we get? So we have 1 plus 1 is 2, plus, now the degree 1 terms are x1 plus x2, plus, and the degree 2 terms are x1 squared plus x2 squared, plus higher terms. Now it's relatively easy in this case to write this as a polynomial in the elementary symmetric functions, because this guy is the first elementary symmetric function. And here, let's see, how do we write this? So this is a power sum. And in fact, we always get power sums here if we do this construction, right? So if we take the sum of this power series, we always get so the j's term in this sum will just be gj times the j's power sum. So we need to know how to express power sums in terms of elementary symmetric functions. And in this case it's easy. So let's take sigma 1 and square it. Then we get the square of this, which gives us this term, but we also have mixed terms. So we have 2 times x1 times x2, which we need to subtract. So which means we need to subtract 2 times sigma 2. Now sigma 2 is exactly the mixed term, plus higher terms. And so we see now we can read off the alphas. And so we see alpha 1 of plus 1 is equal to, so we just have 1 times sigma 1, so it's just this 1. So we need to we're looking for the polynomial into which we have to insert the elementary symmetric functions to get these expressions. And alpha 2 variables, is equal to, then I have this term to consider, so I have s1 squared minus 2s2 on 2. And you see, if I wanted to compute alpha 3, then I would have had to take at least 3 variables and just push the extension to include the cubic terms. Good. All right, so these are the 2 first terms in the additive sequence of the exponential series. And that one is important because it leads to the Chern character of the bundle. All right. And so what exactly is the relation now? So that's purely algebraic here. Let C equal 1 plus C1 plus C2 and so forth be an element in our grade algebra. And then I want to re-express the term which I use to define the additive class, which is this term. And of course only the second part is just this term. Can be expressed as, well, so let's say we stop here to Cn. Then, so this term that we're looking for can be written as sum, or maybe we don't have to stop. Then we have to just take the sum all the way up to infinity. In reality, it would be finite, of course. Take alpha k on the additive sequence and insert these elements up to the kth one. So that's the relation. So in other words, if you want to compute the additive class, for example, so for the exponential series, for instance, it may be a good idea to first determine the additive sequence for that power series. And if you know the Chern classes, you can just plug them in. Okay, so let's put it. All right. So, well, we remember that the Chern classes were obtained by taking the curvature matrix with a connection with respect to some frame, some periodization, and we inserted it into the determinant, and then this gave us a form that represents the corresponding Chern class. And to this, we want to apply this algebraic procedure of doing this construction. So let's do this again for matrix. First, not for the curvature matrix, but for scalar matrices. For the diagonal matrix at first. Let's do this first. And so that's a diagonal matrix. Complex entries, or in the general case, entries in our let's do it in the complex case, doesn't really matter. And okay, so let's see. So the polynomial, the invariant polynomial into which we have to insert the curvature form is this. Right? It's the determinant of the identity matrix plus, and then we have the curvature matrix normalized by 2 pi I. So let me do this with such a matrix first. And I want to consider this as a polynomial in the lambdas. So that means, in fact, I give the lambdas degree 1 here. So in reality, so they are complex numbers, but my graded algebra now consists of copies of complex numbers here, where the lambdas sit in A1. So this will implicitly be used in the computation. Okay, so what do we have here? So this one, so the determinant of this diagonal matrix here is then just the product of 1 on lambda j. Right? This we insert, and later we will replace the diagonal matrix by the curvature matrix to get the Chern character. And well, what's the algebraic procedure now? Now we have that, the C, and then we have to apply the logarithm to it. So let's apply the logarithm to it. This, if I apply the logarithm to this, then this will convert the product into a sum. And then I have the logarithm of this term. Which is nothing but by the series of a logarithm. So that will be lambda j minus lambda j squared on 2 plus lambda j cubed on 3 and so on. So that's what we get when we apply this logarithm to it. And then we have to apply this lambda g to it. What does that do? Well, lambda g is linear, so the sum remains the sum. And now, there's the definition of a lambda g. Where do I have it? Here I have it. So what does it do? It multiplies in degree j. It multiplies by j. This removes these denominators here. And it multiplies with the sign. This removes this alternating sign. And then we have to multiply with g in addition to that. So what we get is simply g1 lambda j plus g2 lambda j squared plus g3 lambda j cubed, etc. Right, so that's what we get. And this is nothing than inserting lambda j into the power series. Continue the computation here. So what we have, this is equal to sum j equals 1 to n. Only the 0 degree part is missing, and the 0 degree part will be 1. So I have to subtract this one, and then I can replace this one by g of lambda j. Right. And this, of course, exactly the n that we have on the other side here. And we write this as minus n plus. And now, if the lambda j's are the eigenvalues of this diagonal matrix, I apply g to it, to this power series, and I take the sum. The g of the lambda j's are the eigenvalues of the matrix that I obtain when applying the power series to the diagonal matrix. And then I sum over the eigenvalues, so that's nothing but the trace. So what we have here is the trace of g of this diagonal matrix. All right, good. And so that's for diagonal matrices. Now, by invariance of the determinant, the same thing holds true for diagonalizable matrices. So the determinant of one identity matrix plus any A is equal to minus n plus trace of g of A if A is diagonalizable. And by continuity, since diagonalizable matrices are dense in all matrices, this remains true for all matrices. Same formula is still true for all A. And if it holds for all complex matrices, it holds also for all matrices from some algebra, as we know. Therefore, the determinant of one, this is not determined itself, it's logarithm and then lambda g applied to it. So that's the left-hand side. That's something that I'm computing. Apply the logarithm and then lambda. So also here, lambda g log det, lambda g log det, 1 plus omega normalized by 2 pi I will be minus n plus trace of g of omega by 2 pi I. So that's this remark I make for later purposes. But here we are still on the entirely algebraic part. So what this now tells me is where do I have it? Here, for this one, taking this one here, lambda g log of c will then be minus n plus, and here I have exactly the definition, so I can write this sum here by the definition of additive sequence in terms of the additive sequence. So this is then, this one is then given as the additive sequence coming with this power series. So alpha k of sigma 1 of lambda all the way up to sigma k of lambda. And yeah, this is well, this is just as C1 and this is Cn. So this proposition has nothing to do. This is algebraic. So that's why I put this into parentheses for the moment. So I just do the computation until I do it here, and then from this I conclude that. Yes, I got ahead of myself a little bit because I will need this in a moment. But for the moment, it's an entirely algebraic thing. Can be applied to the Chern class of a complex bundle. Can also be applied on the eigentypes of a real bundle. No, just ignore this for the moment, but I'll come back to it in a moment. Then I don't have to redo the computation. Good. So we have that. So that's an alternative algebraic. So both things are entirely algebraic. Both expressions are entirely algebraic, right? And I just showed you that they are the same thing. Whether you start with this construction I explained last time, or whether you start with the corresponding additive sequence, doesn't make a difference. It's the same result. For any graded commutative algebra and power series starting with 1. Alright. Don't ignore this for the moment. So just continue the computation here. Then there's no determinant appearing. But yes. But I mean, this is, yeah, the determinant. That's just the logarithm. I mean, the logarithm series applied to this one in terms of the coefficients of a, right? So the determinant, if you consider this as a polynomial in the entries of a, then this is a polynomial that starts with 1 plus higher terms, and you apply the logarithm series to that, which I have maybe somewhere on the board still. So this is, I'm using this formula, right? Logarithm of 1 plus y is equal to y minus y squared on 2 plus y cubed on 3 and so on. And then you would just insert the matrix A into the series. All right. And so from this computation with the curvature matrix, I can conclude another way to compute the additive class, which is the next proposition. So that now we are really in the geometric context of F be a vector in the C bundle on N. Then Fg, as before, is such a double power series. Then the additive class of F associated with this power series G is represented by the following differential form. Take the curvature matrix of a connection, normalize by 2 pi I, insert this into the power series. Note that this will give a finite expression. It is an infinite power series, but this omega is nilpotent because if you pass the dimension of the manifold, this has too high degree for the differential form, or actually manifold on 2. So this gives a matrix. So the whole thing is a matrix with whose entries are mixed differential forms, right? Differential forms of various degrees. And now you take the trace of that, and you get not a matrix of differential forms, but differential forms. And this represents the additive class. So where omega is the curvature matrix, the curvature form of a connection on F with respect to some localization. But if you change the localization, we know already that it does not change. So that's a globally defined form. If you change the connection, it does change, but the cohomology class represented by it does not. Good. So that's the proposition. And that's what I have actually already computed here, right? So we've seen that if I do this not on the level of cohomology, so if my graded algebra is not cohomology, but it consists of forms rather, complex forms in this case, like this. So if this is my graded algebra, then the computation, the previous computation has shown that lambda g of log of a representing form of the Chern class, which will be the determinant of the identity matrix plus omega of 2 pi. So that represents the Chern class, so the whole thing represents this additive class if I add the zero order term to it. Then this computation that I had done here already shows that this gives me the trace of g of omega on 2 pi I, which is the claim here. And then you pass to the corresponding homology class, and then you have the additive. All right, so that's the proof. So that's a useful formula if you have a bundle and a connection on the bundle, you want to compute the additive class directly without first computing the Chern class. So then you can do this, you can compute this matrix and trace it, and then you get your, for example, the Chern curve. If you want to compute the Chern curve directly without first computing the Chern class, that's the way to do it. Okay. Coming back to or applying this proposition, this algebraic proposition here. So we have computed the additive sequence to the exponential series somewhere. Maybe it's It's still there. It's all there, all the way up there. So we could apply this now, of course. So this tells us, according to this one, that the Chern character of a bundle, of a complex bundle, so that's a complex rank n bundle. So this starts with the rank of the bundle, so the fiber dimension, as zero order term, plus, then I have to take alpha 1, which is just S1, and into S, and in this polynomial, I have to insert the Chern class. So that's C1 F. And for the second, so that is then the degree, yeah, it's homological degree 2, but in this gradient, it's the first term that appears. And for the second one, I have to take S1, which is C1 of F, first Chern class, squared, minus 2 times second Chern class, plus higher terms. Right. And this is the second part occurring in the expansion of the Chern plus higher terms. So in particular, notice that the first Chern class and the first Chern character part, they are the same. And in fact, you also see that due to these coefficients in the power series, here we are using the exponential series, we have these coefficients in the terms of these Chern character terms. This makes the Chern character no longer an integral homology class. I mentioned earlier that the Chern class itself is integral. If you integrate it over a submanifold, then it will give you an integer. That is no longer true for the Chern character, because of these denominators that pop up in the exponential series. All right. Good. Yeah, because the exponential power series is a rational power series, yes. That's why only rational coefficients occur. That's true. Yes. All right, good. And now comes a special property of the Chern character which distinguishes it from other additive classes. Position. Namely, so let F and G be complex vector bundles on a manifold. Then we know that it's an additive class. So if we take the sum of the two bundles, then the Chern character applied to it is the same as the sum of the individual Chern characters. So that's true for all additive classes, no matter what the exponentials, no matter what the power series. But in this case, we have an additional property. Namely, we can also look at the tensor product of these two bundles and take its Chern character. And then what we get is that this is the product of the individual Chern characters. This is something which is not true for general additive classes and which makes the Chern character special. So let's see why this is true. So it's not only additive with respect to direct sums, but it's also multiplicative with respect to tensor products. And if you want to express this in a fancy way, then you would say the Chern character sets up a ring homomorphism from K-theory to cohomology. But this means nothing else but what I'm saying here. And why is that true? Let's see. Well, we are free to choose any connections on our bundles and to compute the representing forms. So let's start with the connection of F and G. So let nabla F and nabla G be a connections on F and G respectively. And now let's see. So there's an induced connection on the tensor product. Nabla F tensor G on the tensor product of two bundles, characterized by the Leibniz rule, characterized by the following rule: the tensor product connection in some direction x, so x is some vector field or some tangent vector m, and I want to apply this now to a section of the tensor product. Such section can be written as linear combinations of fewer tensor products, and so it's by linearity, it's by the general rules of connections, it's sufficient to specify what it does on such products. And what it does is it has a Leibniz rule. So we first differentiate S tensor T plus S tensor the derivative of T. Alright, and so that's can be used as a definition of the connection of the tensor product. Now what does this mean for the curvature? Because that's what we are interested in. The curvature has to be inserted in our variant polynomials. First, for the curvature tensor, for that connection. So what does it mean? So then we have to apply this twice, right? We have to apply this twice. Then we get terms where both nablas hit S, and we get terms where both nablas hit T. So this gives us curvature on S and identity on T. And the other term would be identity on the S term and the curvature of G on T. And then in addition we get mixed terms, where we have a nabla X here and then for F and a nabla X or Y there for the other term. But since this is a skew symmetrization, these mixed terms cancel. So this we are just left with this. So the mixed terms cancel. Okay, so we have that. So what does this mean for the curvature matrix if we choose a frame? Now the law of localization. So choose local frame S1 all the way up to Sn1 for F and T1 all the way up to Tn2 for G. Then we get a frame for the tensor product bundle by just taking tensor products of these things. Then Si tensor Tj is a local frame for tensor product bundle. Now if I express the curvature matrix in these frames, then I get a corresponding curvature matrix also in that frame. So that would be omega F tensor G. And what is it? Well, then it will just be omega F tensor identity plus identity tensor omega G by this first formula. And so that's what we get. And then we can see what happens if we apply the exponential series to this curvature formula. So the exponential, because this is what gives rise to the Chern character, right? So the trace of the exponential series applied to the curvature matrix, normalized by 2 pi I, gives us the form representing the Chern character. So what would that be? It's the trace of exponential series applied to this guy. Omega F tensor Let me write it like this: omega f divided by 2 pi I tensor identity plus identity tensor omega g. Note also that these two matrices commute. Matrix tensor identity and identity tensor matrix, they commute, because if you compose them, this term will always just be composed with identity and conversely. So they commute. That's something important to know. So they commute. Important to notice. And then if you have two commuting matrices and you apply them in the exponential series, then this exponential law applies. So that means this is the same thing as exponential of the first term times exponential of the second term. And here, this is the step where the special choice of exponential series enters the game. This is what makes the Chern character special. Right? It was defined using the exponential series. So this holds only for commuting matrices. Alright, good. So, but that is, if you have this, that's nothing but, if you look at it, if you take powers of this, then the identity will always be reproduced. So that's the same thing as exponential of omega f 2 pi I tensor identity times, and similar here, if you insert this in the exponential series, the identity term doesn't change. So then you can write this like this. And now let's just multiply the two things. So we get. Now what I'm claiming is that this is the same thing as the trace multiplied. Times the trace of this other one. Why is this? Well, if you, instead of taking a curvature matrix or the exponential of it, you take any diagonal matrix, then here the eigenvalues, you have some eigenvalues which get multiplied by, so you have eigenvalues here. So the trace of the tensor product is the same as the product of the traces. That's just what I want to say. And the reason is that if you have a tensor product, then the eigenvalues are A has eigenvalues lambda j, and the matrix B has eigenvalues mu j, mu k. Then A tensor B has eigenvalues lambda j times mu k. And if you sum all these over j and k, that's the same thing as summing lambda j times mu k. So the trace of the tensor product is the product of the traces. Holds for all diagonal matrices, holds for all diagonalizable matrices, holds for all matrices, and then it holds also for these matrices. Okay? So that's the justification for this code design. And that's the proof. So this is of course important, and this is why the Chern character is basically the only really interesting additive class. We will come to multiplicative classes in a moment, and for multiplicative classes we have several important case examples. But as far as the Chern character for additive classes go, the Chern character is the one that always pops up because of this special property. Okay, so let's see the remark. So what this tells us. So for example, so let's see, if we take the tensor product of two bundles, then, well, what? So we have seen that this is the same as the product of the Chern vectors. Now this can be expanded. The Chern character starts with the rank of the bundle. The rank of the tensor product is of course the product of the ranks. So this is the rank of F times the rank of G. So that's a zero order term. Then we get to the one order term. Plus higher terms. And similarly here we have the rank of F plus first part of F plus higher terms times the rank of G plus first part of Chern character of G plus higher order terms. And now we, or maybe let's multiply this out, so then we get rank of F times rank of G, which coincides with what we have here, that's good, plus, now the first order term will be obtained by taking the rank of F times Chern character 1 of G plus the rank of G times Chern character 1 of F plus higher order terms. And now we recall when we computed the additive sequence of the exponential series, we noted that the first part of the Chern character is the same as the first Chern class. So this is the same, what we have here, as zero order term plus first Chern class. So there is no difference between Chern character and Chern class concerning the first one. And similarly down here, so we have the product of ranks plus, and now we have rank of F times first Chern class of G plus rank of G times first Chern class of F plus higher order terms. So now if we compare, we see that the first Chern class of the tensor product is given as the rank of F times the first Chern class of G plus the rank of G times the first Chern class of F. And in the case of line bundles, where the rank is equal to 1, this just tells us that the first Chern class of the tensor product is the sum of the first Chern classes. And that was an exercise on your sheet. So for rank F and G equal to 1 for line bundles, we know we deduce this thing that we have all proved on the exercise sheet, namely that the first Chern class of the tensor product is the sum of the first Chern classes of the individual bundles. That's just a side remark. And now we see that this is just a little special case of the fact that the Chern class has this multiplicativity property. The Chern character has this multiplicativity property. Good. All right. So this is all what I wanted to say about additive classes. Now we come to multiplicative classes. Now we come to multiplicative classes. So again, we start with the Butler series. This time I call it F. Now for C means 1 plus C1 plus C2 and so forth in an element in our graded algebra. So that could we could always do this also for the algebraic part. We could also do it for the direct product rather than the direct sum. which would mean that infinitely many of the components can actually be 0, because in each fixed degree we only have finite expressions. Yes, anyway. But let me stick to this, because for our application this is good enough. And yeah, then we can do the following thing. So again, start with C, insert it in the logarithm series as before. And now we apply lambda, but I'm not for the power series f itself, but rather for the power series logarithm of f. Where we do exactly the same thing, right? We apply the logarithm series that we had on the blackboard before to this term. So, right, so we chop off the 1, and then we have this term minus this term squared on 2 plus this term cubed on 3, etc. And then we sort by homogeneous components. This gives us a new power series, which is the logarithm of f. It does not have a zero order term. Well, this starts with x, this power series. And so insert it here, and then the result is put into the exponential series. Oh, okay. So that's what we do now. And then, so this is the algebraic construction. So the multiplicative class of C, or the multiplicative element in this algebra, element of C associated with this power series f. And we will apply this to the Chern class and also to the multi-item class later. And well, so we can describe this construction. Why doing it exactly this way? We can describe this construction also using a multiplicative series now, rather than sequence, rather than an additive sequence. And this goes as follows. So this time, so when we discussed additive classes, what I did was to insert variables xj in my power series, and then I summed them up and got something symmetric in the xj's. And this time I multiply them. Then again I get a symmetric power series in x1 up to xn as before. And the homogeneous part of degree k of that thing can then again be written as a unique polynomial in the elementary symmetric functions, just as before. So there exists a unique polynomial, which I now call uk, polynomial in k variables, such that the homogeneous degree k part of the symmetric polynomial in the x's is nothing but uk of the elementary symmetric functions in x. So it's exactly the same thing as we did before, except that instead of summing, I multiply the power series. And as before, by the same reasoning, this does not, so uk does not depend on n as long as n is at least k. It's the same argument as before. And then the sequence of UKs, so this is called the multiplicative sequence. Associated with this power series f. Alright, let's do this in an example before we come to characteristic classes. Example. So what's the power series f that I want to take this time is the so-called Todd series. So f of x in this case is given as x divided by 1 minus e to the minus x. So now we have to first think a little bit why this is a well-defined power series. Why this is a quotient of series actually. And well, I could argue, well, this is a smooth function. It's also smooth at x equals 0, and I take its powers, its Taylor series. But I can also do the manipulation entirely in the space of power series. So let's see what is this actually. So I could rewrite this as follows. I have x on. Now here, if I start the series expansion, then the first term will be 1, which will be cancelled by 1, right? So well, what we actually have is minus, and then I have the exponential series of minus x. So which would be minus x plus minus x squared on 2 plus minus x cubed on 3 factorial, etc. So this is if I compute the denominator, and now we see that the x can be cancelled. So I can write this as 1 on, and then I have a 1 starting here, then I have this minus, this gives a minus x on 2, this gives me 3 minuses here, 1 minus here, plus x squared on 6, etc. Higher terms. And now I have something 1 on a power series which starts with 1. Such power series are invertible in the ring of power series. I can just apply the geometric series to this remaining part and expand it. And if you do it, I have to look up what we get. It's 1 plus x on 2 plus x squared on 12 and higher terms. So that's what we get. So this is the power series I'm actually working with, right? Okay, good. So that's the Todd series. And let's compute the associated multiplicative sequence for it. How do we do that? Well, let's want to compute u1 and u2 again. So then we need again to take at least 2 variables. So choose n equals 2, that will be fine. And so what we have to take is take this power series, f of x1, and multiply it with f of x2. Compute what we get and sort by homogeneous parts and express those in terms of elementary symmetric functions. So let's do that. So I use this part because the higher terms don't matter for u1 and u2. So I have 1 plus x1 on 2 plus x1 squared on 12 and higher terms times same thing for x2. Alright, so this will be 1 times 1 is 1 plus now 1 times x1 plus x1 on 2, well, so this gives me x1 plus x2, 2. So this is the first order term, and then I have quadratic terms. So what I get is first this power sum coming from these terms, but I also have one term coming from the 2 first order terms. So this will give me x1, x2 on 2 times 2 is 4, plus higher terms. And now express this in terms of elementary symmetric polynomials. Alright, so this is 1 plus. Now the first order term, that's easy to see, right? That's just the first symmetric polynomial. And now this one, again here I have a power sum. So the power sum can be obtained as the square of the first one, and then I have to subtract the mixed terms, which is minus 2 times the second. 12 plus, and this term is just the second polynomial for plus higher order terms. So that's what we have. So this is 1 plus sigma 1 x on 2 plus. Now, so what happened? We have So sigma 1 of x squared on 12. Now here we have minus 2/12 plus 3/12 will give me minus plus 1/12, right? So then this would be plus sigma 2 of x. Minus 2 plus 3 makes 1 plus higher order terms. So that means mu1 is s1 on 2 and mu2 is s1 squared plus s2 on 12. Check, looks good. So that's the multiplicative sequence for the Todd series. All right, good. And now the proposition, which is completely analogous to what we have for the additive classes, says that this prescription to produce a new element in the Gauss algebra can be also expressed in terms of the corresponding multiplicative sequence. So for C equals 1 plus C1 plus C2 and so on, in A equals A0 plus A1 plus higher ones, we have that this prescription that I have on the board, exponential applied to endomorphism related to the logarithm of Pausing's log f, applied to log of c, is the same as the 1 plus the sum of the corresponding multiplicative elements of the multiplicative sequence, where I insert C1 up to Ck into it. Good, so let's also check that quickly. And this then somehow explains why we have to take a logarithm of f here. Let me do it for diagonal matrices first. So again, for C of the form 1 plus a diagonal matrix, so where this is to be considered as of degree 1, log C will be what? So that will be the logarithmic series applied to this guy. So that is the diagonal matrices where I insert the logarithm. So the logarithm series for lambdas, which is lambda j. So yeah, so I apply logarithm to each term here. Lambda 1 minus lambda 1 on 2 plus the squared plus lambda 1 cubed on 3, etc. It's just applying the logarithm series to 1 plus lambda 1, and similarly for the other terms. Like this, then, yes. Now let me do the computation for this in a moment, and then, okay. So then, so it's the logarithm of the product of 1 plus lambda j, right? So as before, this is the sum of the logarithm series of this one, log 1 plus lambda j, which is the sum, and then we have lambda j minus lambda j squared over 2, etc. That was the series I had before. Now let's apply lambda log f to it. Then we get the sum of, so here I have to multiply with plus 1 times lambda j times j times the corresponding part in the logarithm series, right? So the j goes away. This is not that j. It's 1 in this case. So that's logarithm of f, the first term, times lambda j. And now here we have plus logarithm of f, the second term, the minus 1 and the minus 2 are corrected by this lambda term, so that we just get lambda j squared, and so on. So in other words, what we have here is nothing but the logarithm series of f applied to lambda j inside. So that's what we get. And now we apply, well, the final thing we want to apply is the exponential series here. So this will convert the sum into a product again. And then we have exponential of the logarithm of f of lambda j, which is of course nothing but the product of f of lambda j. So that is, by our construction of the multiplicative sequence, the sum 1 plus the sum over k of mu k of sigma 1 of lambda all the way up to sigma k of lambda, and which then will be 1 plus sum over k mu k of c1 up to ck. And the rest of the argument is the same. So this is for all matrices you can, and then you have it for all elements in the So this proves the relation for matrices in complex matrices, and then and so on. So this is the alternative to computing the corresponding multiplicative class. And since we just computed the multiplicative sequence for Todd series, we find that the corresponding characteristic class, so that is a vect and C bundle, then the Todd class of F, which by definition is the multiplicative class of F associated with the Todd series. So for this one we get that the first part can be expressed in terms of the Chern class like this, so that is the Chern class of F divided by 2. And the next one is given by this expression, so it's the first Chern class of F squared plus the second Chern class of F divided by 12. And for the higher terms, you would need to expand the multiplicative sequence to higher degrees, which is just a standard computation, of course. Why do I care about these classes? So let me give an example. These classes pop up in applications, in particular in so-called index theorems. And index theorems are actually quite common in various branches of mathematics, which has been understood only over time. And one of the classical ones, which is much older than index theory, is the so-called Riemann-Roch theorem, or in the form of that I will give it in a moment. It's also due to Hirzebruch. That's the Riemann-Roch-Hirzebruch this as an example. I'm not going to say much about, just to give you an idea of where this kind of thing is used. So let M be a compact complex manifold. Let F be a holomorphic vector bundle over M. I'm not defining. I'm not going to define what a holomorphic vector bundle is. It's a complex vector bundle with an extra piece of structure, which is not really so important for us. Then, to this you can associate so-called cohomology theory, which comes in pi degrees. So H, P, Q, M, E. So they are defined by Riemann-Roch homology. Just take a moment. And then if you take the alternating sum of some of these so-called Hodge numbers, where the Hodge numbers, namely 0 from Q from 0 to the dimension of M. So that's a little bit like an Euler number, right? So you have an alternating sum of certain. If this was a Betti number of a manifold, then this would just be the regular Euler number. And here that's the holomorphic cousin of the Euler number. You can replace the Riemann homology by a complex version, which is called Dolbeault homology. It comes with a pi degree, and so but if you take this alternating sum, that's sort of a holomorphic Euler number, if you like. And this one can be expressed as you take the Todd class of the tangent bundle of the manifold. It's a complex vector bundle because it's a complex manifold, so this Todd class is defined. You multiply this by the Chern character of this holomorphic bundle F that you have here in addition to that. And then this gives a homology class. And you pair this with the fundamental cycle of M, which means nothing but that you take a representing differential form and integrate it over it. Yes, thanks. So that's the Riemann-Roch-Hirzebruch theorem. You can think of this as a complex variation on the Gauss-Bonnet theorem. The Gauss-Bonnet theorem computes the Euler number of a manifold by some curvature terms, and we will see how to interpret this in terms of characteristic classes later. And that's something where these classes pop up. And there are other classes, I don't have the time to mention them now, I will do this in the next lecture after the break, where other multiplicative classes pop up. We see the Chern character comes here, the additive class, to this bundle here, and the Todd class, which is a multiplicative class for the tangent bundle. And we will see similar formulas like in the Additive index theorem and also in the Hirzebruch signature theorem. But this I will explain next time. I'm not going to say more about this. I'm not going to explain what Riemann-Roch homology is, and these are just the dimensions of the Riemann-Roch homology spaces. And I'm not going to say anything about the proof of it, but I just want to indicate this so that you have seen it, how these characteristic classes are used. So they are really important, and that's why I spent so much time on it. So my time is up. I thank you for your attention. I will wish everybody a nice Christmas break, and so I hope to see you all again on January 3rd. Thank you.